Hey folks, I'm hoping everybody's doing well. Welcome to this presentation brought to you by myself, Joaquin, Crystalline, and Aaron. Today we're going to be covering the last group on the periodic table, the noble gases.
The group 18 elements are traditionally designated as the inert or rare gases, however they no longer satisfy these early labels due to advances in science which have proven this to not be entirely true. The elements which make up the noble gas group are helium, neon, argon, krypton, xenon, and radon, all of which are characterized by having a filled valence electron shell which contributes to their unreactive nature, as can be seen in the figure on the right. These elements went fairly under the radar of scientists up until around the mid-1700s due to their inert characteristics. However, the Cavendish experiment of 1766 created the first experimental evidence for the existence of the noble gases. In this experiment, Cavendish demonstrated that a small unreactive fraction of gas remained after removing all known components from a sample of air. This unreactive fraction remained a mystery for more than a century. However, it was eventually discovered to be a mixture of argon and other noble gases. Following this, helium was discovered in 1868 when it was identified from spectral lines observed during a solar eclipse, leading to the proposal of a new element. This discovery was later confirmed in volcanic gases released from Mount Vesuvius to be helium. Argon gas was then discovered in 1895 when Lord Rayleigh and William Ramsay discovered discrepancies between the density of nitrogen, which was isolated from a sample of air, as compared to the density of nitrogen, which was isolated from a sample of ammonia. This led to the isolation and discovery of argon. Further discoveries continued to happen from 1898 to 1902, where within those few years, scientists isolated additional noble gases such as neon, krypton, xenon, and then finally radon was identified in 1902 as a decay product of radium. When examining the noble gases, the group trends tend to roughly follow that of the periodic table. This can be seen in the figure quantitatively, in which as the atomic radius increases or as you travel down the group, the ionization energy is seen to decrease, which is expected as it mirrors the periodic trend. Along with this, as the atomic size increases, it can be seen that the boiling point and melting points are also seen to increase. This is also expected as it does mirror periodic table and its trends. One thing to note is that as you travel down the group, the electronegativity decreases following the periodic trend. However, helium does stray from this since as the first molecule of the group, it would be expected to have the highest electronegativity, but in reality it is slightly lower than that of the element below it, neon. This is due to its lack of a valence p orbital, or since its outer shell only consists of an s orbital or two electrons. This then would be compared to if it was to have a s and p orbital or have 8 electrons. Once past helium, the elements all follow the trend in which electronegativity decreases as atomic radius increases. Outside of the property trends, one notable thing, which is not intrinsic to the trends of the periodic table, but it is interesting living on Earth, is that argon makes up almost 1% of the air we breathe, making it a fairly common element within our atmosphere.
So, in terms of the relationship between noble gases and elements and other groups on the periodic table, noble gases were originally believed to be unreactive because they have a full set of 8 electrons. Um, However, noble gases do have some reactivity with some other compounds. For example, they can form clathrates, and clathrates are a type of crystalline structure where uh, molecules form, I guess, kind of like a cage-like structure that can trap a smaller molecule inside of that cage-like structure. And in the case of noble gases, water or solutions that contain hydroquinone can be crystallized under high pressure to create a crystalline structure that can trap either argon, krypton, or xenon. However, helium and neon are too small to become trapped and they will escape through that crystalline structure and they cannot form clathrates. Additionally, the noble gases, particularly xenon, can covalently bond with other atoms to create adducts. And most of the time, this occurs with xenon. Those are the most diverse um, adducts with any of the noble gases. Here in this table, we have some of the relationships between xenon and elements in other groups, particularly in fluorine. So xenon can create adducts with a different number of fluorines and can either take on a +2, +4, +6, or +8 oxidation state, depending on how many lone pairs are on the central atom and how many fluorines and oxygens that the xenon is bonded to.
Let's take a look at some more widespread applications of the noble gases, starting with lamps. Neon lights are really popular, but the other gases also emit their unique colors of light, and because their ionization energy is so high, it's really safe to use the noble gases as sources for emission because you don't have to fear about side processes occurring when you put the atoms in their excited state. Slightly sillier of an example would be balloons, particularly helium balloons being very popular. And while being lighter than air, they are not as explosive as hydrogen gas, which is convenient when you're not trying to turn a birthday party into a recreation of the Hindenburg. Additionally, noble gases are really popular in industrial settings, like argon being used in a lot of industrial processes because an inert atmosphere is advantageous. Chemical storage is one of the very many uses of argon because if you have ever conducted chemical research or if you are in industry, you know that a lot of our sources and a lot of our reactants can be air sensitive and particularly water sensitive. And keeping something under an argon or a noble gas in general uh, minimizes the loss of reactants to that sensitivity. Krypton, radon, and xenon can form fairly stable compounds acting as oxidizing agents, and that can be particularly useful in, once again, chemical synthesis.
Another important application of noble gases, particularly in characterization and in the chemistry field, is in ICP-MS. So ICP-MS is inductively coupled plasma with mass spectrometry, and it's a way of characterizing elements that are in a sample by ionizing the elements under plasma, and then those ions will travel to a mass spectrometer, which will characterize them based on their size and charge. And this will allow chemists to essentially understand what elements are present in their sample. Um, the plasma that is used in the inductively coupled plasma is made of argon, so it's an argon plasma. And the way that argon is turned into a plasma is by exposing it to a very strong electric field inside of the torch in the ICP-MS. And the argon is ionized to help sustain the plasma. And because argon has such a high ionization energy, this means that it can atomize most elements on the periodic table to carry out this ICP-MS.
One fun fact about the noble gases is that they can be used within planetology or the study of the planets in our solar system. The noble gases are known for their inert nature, in which they don't easily form compounds with other elements. This makes them actually excellent tracers for studying planetary atmospheres because they don't react or bond with other gases, allowing scientists to detect them in their purest forms. Uranus is known to have distinct clouds of xenon in its atmosphere, which puzzled scientists due to xenon's rarity within our solar system. While most planets have noble gases like helium and hydrogen in their atmospheres, Uranus stands out because it has an unexpectedly high concentration of xenon. This leads many to question about the formation and evolution of the planet. Xenon plays a crucial role in understanding planetary formation. Xenon, like other noble gases, can act as a time capsule, giving scientists a peek into the early solar system. And then by studying the composition of xenon in Uranus's atmosphere, researchers can infer how the planet might have captured gases or what processes might lead to the planet's distinctive atmosphere. And then furthering upon this, these findings are important since they give us clues into how Uranus, along with other ice giants, were formed and evolved. And then differences in xenon concentrations, like can be seen in the figure, might suggest that Uranus's atmosphere development was then formed differently from that of Jupiter or Saturn.
Now, if you're like me, you've wondered, why does inhaling helium make me sound like Alvin the Chipmunk? And the answer isn't necessarily that it makes the frequencies you create with your voice higher, but rather that it amplifies the higher frequencies while dampening the lower ones. Your voice is created by your vocal cords, yes, but the vibrations that your vocal cords create in the air are propagated in the voice box. And when you inhale helium, a large portion of that voice box is occupied by the helium gas. Since it is lighter than air, it allows the higher frequency sounds to pass through it to propagate much quicker than the deeper noises that your voice typically creates. What that effectively does is act as a frequency filter. The lower sounds that you're creating with your voice get trapped in the voice box, and it lets the higher frequencies out much better. And that's why if you inhale helium, you sound like an anthropomorphic rodent.